Hi everyone! This video is going to be all about the concept of ideal gases. When you hear the phrase ideal, oftentimes we think like perfect or like as best as it can be. And that's essentially what we're getting at when we use the phrase ideal in combination with gases. Through the year, whenever we say the term gas, you probably think a particular diagram. And what pops into your head is exactly how we're going to try and describe the motion and behavior of an ideal gas. Because when we say the word gas, it's most likely you're thinking something like this: spacing particles really far apart, having them bounce around, moving pretty fast. That's what we believe a gas to be like. And there's something that backs us up in that conception, and it's called the kinetic molecular theory, or KMT. It's a phrase that'll sometimes pop up, but what's really noteworthy about it is that it tells us exactly what we already know about gas molecules, that they move in straight lines, and their movement is constant. Moreover, all of this movement going on in here results in no attraction between particles. So when we talk about the intermolecular forces of substances, we can actually assume that there's no intermolecular forces that exist between gases. This ultimately arises because of this huge space that we put between our gas particles. So enormous amount of space between particles. So much so that the actual size of the particle itself doesn't even matter. The Regents exam calls that negligible. It doesn't matter how big or how small the particle is, because the space between those particles is so much bigger. And last but not least, we describe ideal gases as never losing energy. No matter how many times they collide with the wall or with each other, we call those collisions elastic. They're just going to keep on moving at the same speed they started with, or at the very least, they'll transfer that energy, and no energy is lost in our whole system. All right, so this just tells us exactly what we already had conceptualized about the behavior of gases. Now, it's not always true that gases are going to behave in this particular way. But when we talk about gas calculations and just general gas behavior, these are a series of assumptions we make. And those assumptions are most likely to be true when the temperature is very high, because that helps us get at the constant movement, putting lots of space between particles, no energy loss, and making the particles move so fast that they don't really have time to be attracted to one another. And we can couple that high temperature with low pressure, we're certainly in business, because with low pressure, we have lots and lots of space for those particles to move around. We increase this distance between the particles, so the particles themselves are more likely to follow these rules that we've established for the gas. This little column here on your screen right now is the topic of a Regents question on nearly every single Regents exam, remembering that ideal gases are most likely to sort of behave in the way we want them to at high temperatures and low pressures, kind of like an ideal vacation, a high temperature and low pressure. All of this business really gets to the point that we can make certain assumptions about gas particles that we can't really make about anything else. And if we take a look over in this last column, what we're going to be looking at is actually comparing the number of particles that are filling these two balloons. What I see is that these two particles take up the same amount, these two balloons take up the same amount of space. And this STP label tells me that both of them are at 273 Kelvin and 1 atmosphere, the values for standard temperature and for standard pressure, or at least one of our unit choices for those values. So if these two balloons take up the same amount of space and their atoms are moving at the same speed, pushing with the same amount of force, that means there must be the same number of atoms or particles inside those balloons. I want to be wary of saying the word atoms because sometimes this gas, maybe it's CO2, and maybe over here it's He. These two molecules aren't made of the same number of atoms, but the assumption we can make is that this balloon A contains the same number of particles of helium as balloon B contains particles of CO2. So if pressure, temperature, and volume are the same, the assumption we're able to make because of all this business is that number of particles are equal. Doesn't matter what the identity of the gas is, because we assume it behaves in an ideal fashion, we can make this kind of cool assumption of how many particles might be contained within that vessel.